So, to solve problems, first thing, make sure you convert everything to coulombs. Rarely will I actually give you a charge in coulombs. Typically, it'll be in microcoulombs. So 1 microcoulomb is 1 times 10 to the negative 6 coulombs. That is on your formula sheet in that little chart where I have all the metric prefixes, although probably during this unit, Jess, you've kind of committed it to memory, I hope. Or, instead of giving you a charge, I'll talk about a proton or an electron. You've heard me do it's a proton, it's an electron. So the charge on an electron, the charge on a proton is both the same magnitude. We symbolize it with a lowercase e. That e doesn't stand for electron, it stands for elementary charge. And it is also on your formula sheet. The charge on an electron is negative, so the elementary charge is negative 1.6 times 10 to the negative 19 coulombs. What's the charge on a proton? What's the charge on a proton? Yeah, could you read it to me, please? Yeah, didn't need to look it up, Stephen. At 1.6 times 10 to the negative 19 coulombs, which is why we call this the elementary charge. The two subatomic particles in the atom, if we don't go down to the quark size, have charges of plus or minus 1 elementary charge. Negative 1 elementary charge, negative 1.6 times 10 to the negative 19 coulombs. It's an electron. Positive is a proton. The most common mistake I find, or the challenge I find, Nick, during this is knowing which formula and which unit to use. We're going to fill in the first column just talking about what is the correct variable. So, force. What's the variable on my formula sheet for force? Yep. A little Captain Obvious there. Vector or scalar. Force is a vector, although I don't think I have... Do I have a vector symbol on the F in your formula sheet? No, and that's because we figure out the direction ourselves later on. What are the units for force? Force is measured in? Okay. Another concept we've been talking an awful lot about is field, and I know the word field starts with an F, but F is force. In fact, typically I use another word to describe what type of field this is. What's the variable that we've used for field? Capital E, because it's electric field. It's also a vector, but the vector doesn't show up on your formula sheet. If you look on your formula sheet under electrostatics, I think there are 3 equations that have a capital E electric field in them. The first row, second and third equations. Second row, middle equation. The first row, second equation, and the second row, second equation, Stephen, tell us the units for electric field. The first one tells us, does it not say force over F over Q? Yeah. Which would be newtons per coulomb, right? Newtons, force, charge, coulombs. And the one right beneath that also has an E. How else can I measure electric field from that second equation? Look at it, and what's the first thing on top in that second equation? Not velocity. Not velocity. No, 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 no. It's voltage. Volts per meter. This is why I said last lesson, can't get V and V mixed up. Capital V is voltage, lowercase v is velocity. That's why whenever I handwrite voltage, Stephen, you see me put that for voltage, right? But the type font doesn't do that. You have to know. PE, what does PE stand for? Oh, I was going to snap. It's not electric potential. It's electric potential energy. And yeah, it's not your fault. The names are tricky too. There's a problem. I use PE. What does your formula sheet use for the variable for potential energy? E with a little subscripted P. Energy, potential energy. Which is also wrong, by the way. Really, we should use a capital U. Doesn't work well for the word energy, but it doesn't get anything else mixed up. Why you? Because not all physics was done by English-speaking people. I think it's from Latin. So this kind of irritates me, but not enough that I'm going to retype that formula sheet. That's a digital copy from the government, and to retype it would take me hours, so forget it. What are the units for energy? Yep. It was also, way back when, because we defined energy as the ability to do work, and we defined work as force times distance, it is also Newton meters, especially if the force is constant. I don't think that's going to come up this unit, but I'm enough of a nerd that I should at least mention that's how a joule was defined. It was defined as a Newton meter. Stephen, what letter do I use for voltage? Yeah. Now, to show that it's a capital V, I'll put the little wings on there. Problem. There's another word for voltage. What's the other word that they use? And I will use this word on the test. In fact, electric potential. And you can't confuse electric potential with electric potential energy. There is going to be a question on your test where I say, find the electric potential. And I sadly know some people will say, oh, I'll find the electric potential energy. And I'll even be more specific in a little bit. Don't do that. What are the units for voltage? Well, it comes right from the definition. And Renzo, the definition is on your formula sheet, which you have in front of you, right, Renzo? Can you find, I think it's second line down, first equation? Is that the one that says voltage equals EP over Q? Is that right? And EP is potential energy measured in? Psst. Measured in joules per, and Q is charge measured in. This one you have to memorize. Huh? Yeah. It's joules per coulomb. I think you were right, Renzo. I'm not quite sure, but I'm pretty sure you were good, but I couldn't, yeah. Couldn't quite see your face. Yeah. Okay. Got a latecomer. Pause the video for a second. Are there any other ways we could measure voltage? It's defined as joules per coulomb. I guess it's Newton meters per coulomb, since a joule is a Newton. Yeah. Good enough. Oh, and work. What letter did we use for work? W. And it was typically measured in joules. Okay. Then example 3 says, use the correct equations. So I'm going to actually move all the way across and kind of fill in these rows here. First issue. For forces, how do we find the direction? Matteo, it's pretty simple. 4 words, Matteo. Like. Do we put the positive or negative signs into the force equation? If the charge is negative, do I put in a negative with the Q? Yes or no? Cassidy shook her head. Is she right? And this is why I actually told you put absolute value signs around the Q's on your yellow formula sheet in the first row. Nowhere else, but in the first row. If you didn't do that, you might want to do that now. How do I find the force between point charges? So you ready? Basic rule of thumb. This is a point charge. What shape is a point charge? Don't overcomplicate it. What shape is a point charge? You're looking for a word that begins with the letter C. Circle, think radius, think R. Your equations for point charges typically will have an R in them. If they don't have an R or a D in them, that usually means you can use them for either. So what's the equation for force that has a point charge in it? Hayden, my friend, which one? Yep. Technically, Hayden, here's what I said you could do if you wanted to on your yellow sheet to remind yourself, don't put pluses or minuses in there. We decide the direction by using Mateo, like, unlike, attract. Okay. Hayden, I'm coming back to you. How can I find the force if it's a single charge between parallel plates? Here's your hint. Find another equation that has an F in it. And then get the F by itself, please.
F equals
Yep.
Q over Q.
How would you move the Q over on the same side as the E? What's the Q doing?
Time.
So, can you try that again?
F equals QE.
Yep. What does the letter E stand for? Psst.
Field.
Which field?
Like
Yep, electric field. Okay. Now, the reason I used a lowercase q is this is the charge that's sitting in there experiencing the force. This is like the satellite in orbit, not the big planetary charge causing everything. Okay. What if I have more than two charges? Well, let's call this charge A, charge B, and charge C. Supposing the question said, find the force on charge B. How would I do that? I would find the force of charge A on charge B. I would find the force of charge C on charge B. And I would, for those ones, Jilun, be using KQ1, Q2 over R squared because they're 2-point charges. And then I would take these two answers and I would add them vectorially. Tip to tail, if they were at angles, Jess, like this, if they're in a nice straight line, winner minus loser. Almost certainly, I will give you a setup in a nice straight line on the written section, and it'll either be find the force, find the electric field, find the potential energy. I might give you one at angles on the multiple choice, but I'm really weighing that because I had to shorten the test. I came in yesterday and I shortened the test from the 80-minute ones that I used to give out to the 65-minute ones, so we'll see. Okay. But by add vectorially, what I really mean is, how do I add two vectors together? Luke, draw them. Or if they're in a straight line, winner minus loser. How do I figure out the direction? I use like, unlike. Electric field. Scalar or vector? In fact, that whole first row is your vector row. Okay? So because it's a vector, also no plus or minus sign. But electric field, typically we had the electric field being caused by one charge. So we couldn't exactly use like repel, unlike attract, because there was only one charge. Instead, we defined the direction of electric field. Which way does electric field point? This you have to memorize. We ask if there was a little positive sitting right there, which way would it want to move if it could? How little a positive charge? So little that it doesn't have its own charge. Those of you that have done the bonus video game, which is due Wednesday, by the way, you notice as soon as you add a charge anywhere in the page, it adds an electric field and changes the whole question. So our positive charge, it's positive, but it has no electric field of its own, because that would change the question. If you want a shorter version of that, from positive to negative, because that's which way a positive would want to move if it could, because like repel, unlike attract. Almost certainly there will be a multiple choice question asking you about electric field direction. There will definitely be a written question asking you to calculate an electric field overlapping from from two or more charges. Hayden, I'm coming back to you. How do I find the electric field from a point charge? Well, if it's a point charge, I'm thinking radius r.
E equals K Q over R².
Did you know that, or was Luke bailing you out? Thank you, Luke. And again, Hayden, I would say if you wanted to on your yellow sheet, you could put an absolute value sign there, reminding yourself, do not use absolute values. So our variable for electric field is a capital E. I can also find the electric field between plates. Hannah, how can I find the electric field between plates? Here's my hint. It's a capital E, so find that on your formula sheet, which you have in front of you somewhere, yes? Now, between plates, here's your hint. That is a distance, but it's not a radius. So I would call that distance a distance. How can I find the electric field between plates? However, I'm going to be a bit mean. If I ask you to find the electric field between plates, not only would I give you this distance, I would probably also give you that distance, and one of the answers would use that distance. In fact, probably answer A, if I was giving it to you as a multiple choice question. Okay. Direction here, from the positive voltage to the negative voltage, because that's which way a positive would want to move if it could. What if I have electric fields overlapping? Now, between plates, I can't do that because I guess I could have a plate inside of a plate, but no, it's going to be one plate. But I can certainly have multiple points on the page. So let's call this location here location X. Let's call this charge A. Let's call this charge B. And if I wanted to find the electric field at location X, an electric field is found at a location, how would I do that? Sarah, I would find the electric field from charge A by using KQ over R², magnitude under KQA over RA². I would get a magnitude and a direction. I would find the electric field from charge B, which would be KQB over RB². And then I would take these two and I would add vectorially. Winner minus loser if they're in a nice straight line, or winner plus winner if they all are in the same direction. Here, for this one, they're clearly not in a nice straight line. I'd have to add them tip to tail. If I do give you tip to tail, I flogged sine law and cosine law to death on the momentum test. If there are tip to tail questions, they'll be nice right angles. Unless all I'm asking you for is a rough direction and don't bother doing the trig, then I might feel okay, but probably not. Potential energy, electric potential energy. Direction. What's the direction of the potential energy? And a what? It's a scalar. So at the bottom here, S for scalar, and that means put the signs in. Scalar signs. Put the plus or minus signs in. You can have a negative potential energy. You can have a positive potential energy. If you have a positive potential energy, all that means is if you let that charge go, it will fall. Oh, but of course, it can also fall up, because like repel, unlike attract, but it'll move. If you have a negative potential energy, that's telling you that if you want to get it out to infinity, you'll have to add energy. You have to do work. How do I find the potential energy between 2 point charges? Shayna, what's the equation for that? And here's why this is a challenge. Look up for 1 second. Look up for 1 second means keep looking up for 1 second. What's that equation? Force. And it's easy to even subconsciously, accidentally stick the squared there. Okay? Don't do that. I didn't put absolute value signs because you are going to put the plus or minus signs in. How can I find the electric field between parallel plates when I know the voltage? Sorry, how can I find the electric potential energy between parallel plates when I know the voltage? So on your equation sheet, you have this one, PE equals, no, you have voltage equals PE over Q. And so if I get the PE by itself, it's Q V. That's nice. By the way, Nick, that's the equivalent of the MGH from good old easier potential energy as opposed to the cosmic one. And that's why I've said you can sort of think of voltage as a height. Really, it's sort of like G times the height, whatever the heck that would be, but treat it like a height if you're trying to wrap your brain around it. What would hurt more, Nick? Having one raindrop from 10,000 meters land on your head, or having a swimming pool from 10 meters land on your head? What would hurt more, Nick? Having a single raindrop from 10,000 meters land on your head, or having an entire swimming pool from 10 meters land on your head? Let me try this again. A raindrop or a swimming pool? Which one would hurt more? Why? Not because it's got more height, higher voltage, lower voltage. So the raindrop would have a really high voltage. Voltage isn't what does the damage. What does the damage is also how much charge you're having to absorb all at once. Swimming pool, lots of charge at a low voltage. That's the same as touching a 12-volt car battery. You'll get a pretty nasty shock. Won't kill you, but it'll hurt you. Versus when your door handle sparks, you're probably getting 5,000, 10,000 volts easy there. But so little charge, it's like getting hit in the head by a raindrop. Meh. What if I want to find the potential energy of this whole system? Let's call this charge A, charge B, charge C. What if they said, find the total energy there contained? We would find the potential energy between A and B by going K, Q1, Q2 over R. We would find the potential energy between B and C by going K, Q1, Q2 over R. We would find the potential energy between C and D by going K, Q1, Q2 over R. And then just add them, but they're scalars. No tip to tail. Just add them up. Sorry, why did I go C and D? That's why you're looking puzzled there. C and A. Is that right, Cass? Sorry. And I would either, well, I mean, this, you could use Pythagoras to find that distance without too much trouble, but I'd probably give you that if I gave you that. I would have no problem giving you an ugly-looking diagram with angles and junk for a scalar question where it doesn't make the question any more difficult. It just makes it look difficult, because I do have a fondness for, here's a question that actually ended up being really easy, but it was looking scary. I can teach you that. Voltage. Scalar or vector? This is scalar. So include the plus or minus signs. Same for energy. Same for voltage. How do I find the potential from a point charge? Jess, my joy, how can I find the potential from a point charge? Isn't that force? Is that force? No. E divided by Q? Voltage is E divided by Q? Oh, wait a minute. Okay, let's try this again here. That's the definition of voltage, but look, look, look. What shape is this? From a point charge, give me a voltage equation with an R in it, please. And that's how you can figure, okay? That's my hint to you. Point charges, think instead of point charge, think circular charge. Radius, radius, radius. So try that again. Which one? V equals KQ over R. Good. How can I find the voltage between plates? By the way, that first equation that you looked at, the one that has V equals EP over R, that's the definition of voltage. You actually don't use that specific equation very much. You do get the potential energy by itself in there and use that a fair bit. That's what we did right here. But we give it to the other way because we had to define voltage in the first place. How do I find the voltage between plates? Honestly, usually it's labeled. It just says on the plates. The only time I guess I might ask you to calculate a voltage would be this situation here. Maybe I told you what electric field I wanted and how far apart the plates were, and I said, how many volts do I need, please? Okay. But that's not too tough to handle. Voltage occurs at a location. So let's call this location X. Let's call this charge A, charge B. How would I find the overall voltage at X? I would find the voltage from charge A by going KQA over RA. I would find the voltage from charge B by going KQB over the radius at B. And then just add them, not tip to tail, scalar, add them. Can you have a voltage of 0? Yeah. Because if one charge is negative and one charge is positive, and they both happen to work out to the same number, you'll end up with a voltage of 0. What's that telling you? It's telling you any charge at that location has no energy per coulomb. In fact, really what it's telling you, Cass, is if you put a charge at that location, it would stay there stable. It wouldn't fall anywhere because it has no energy to turn into kinetic energy. Okay? Last one. Work. Really, I just want to talk about how do we calculate work. From point charges, we had to go change in potential plus change in kinetic. If we were starting and ending at rest, change in kinetic was 0. If we weren't, they'd have to tell me the speed. I would have a change in kinetic as well. The yucky part was, because this was going to be K Q1 Q2 over R final minus K Q1 Q2 over R initial. What was the work done if you're moving a charge between plates? This was so much nicer. If you were starting and ending at rest, the work was still the change in potential energy, but what much cleaner expression did we have for potential energy between plates? So work is going to be Q change in V, and that would be the change in energy. Whatever voltage you moved the charge through, that's how much work it took. That's kind of putting everything together. What do I use when? So I wrote on the next page, hey, to solve stuff correctly, make sure you calculate point charge work using energy and not force. And make sure you well, here's what I wrote here. Why can't we use force times, oh, sorry, by the way, little nerd trivia for you here. You can watch, you can write this down if you want, but you don't need to. I could also have gone work equals force times distance. I can only use it between plates because the force is constant, because the electric field is constant. In fact, what was the expression that I wrote further up for the force between plates? This is electric force. What was the expression for the force between plates? So I could write this as Q times the electric field times distance. Wait. I also have an expression one row down for the electric field between plates. What? Hey, what happens to the D's? And I end up with that one there. That one there is an offshoot of physics 11 force times distance, and we can use it because between plates, force is constant. Yay, nicer. And that's really the answer right here. It says, why can't we use force times distance for point charges? Changing force. Why can I use force times distance or QV between plates? So there's a constant force. Example 6 says fill in the vector, add the vectors to find the total force. We filled in the entire chart on the fly. So, example 7. What can I ask you if I give you 2 charges? Well, I guess I could ask you the force between the charges. Better yet, I could pick one of the charges and say, don't just tell me the force, tell me what direction it feels the force. So this says, find the force, magnitude, and direction on the positive charge. Zealand, what does it want me to find? Find the what? Part A?
Direction. Yeah, with the force.
Thank you. Which force? Electric force. How am I going to find electric force between 2 point charges? Julian, which equation am I going to use here? Well, it's got to have an F in it, yes? So find the equations that have F's in them. And then read me the one that has 2 charges in it, because this has 2 charges.
K.
Yep.
Q1, Q2 over R squared.
So it's going to be 9 times 10 to the 9th, that's K. Q1, am I going to put negative 1.5 microcoulombs, or am I just going to put 1.5 microcoulombs? 1.5 micro is 10 to the negative 6. 4.2 micro is also still 10 to the negative 6. How many centimeters between them, Jilan?
36.
So 36 centimeters, 0.36 0.36 meters. Don't forget the squared. What do you get? How many newtons of force between these two charges? I didn't do this one in my head, but I'm going from memory. Is it 0.4375? I should have lied and just pretended I did it in my head. I could have done that one smooth. So 0.438 newtons. Direction. I can't answer that unless they tell me which charge I'm looking at. Oh, they did. They said on the positive charge. So look at the positive charge. Which way is it going to feel a force because of that other charge? To the left, to the right, up, or down? Left. Because unlike attract. I gotta be honest. Part A, that, too easy for written. Maybe a multiple choice, or better yet, as a multiple choice question, I would give you the force, give you both charges, and say, find R. How far apart are they? Get the R by itself. Something like, go backwards, in other words. Rhea, what does B want me to find? Another word for voltage is potential. Okay. At the dot. Maria, I'm going to call this charge A. I'm going to call this charge B. How am I going to find the voltage at the dot? I'm going to find the voltage from charge A first. Then I'm going to find the voltage from charge B next. And then I'm going to add them up. Tip to tail? Nope, just add them up because they're scalars. How do I find voltage from a point charge? Maria, which equation? Yes. So this is going to be QA over RA. It's going to be 9 times 10 to the 9th. Voltage scalar or vector? Include the signs. Negative 1.5. And again, the dumb way to remember that, Hayden, scalar signs, please. Divided by, not 0.36, 0.12, yes, to the dot. How many volts are created at the dot by charge A? It's going to be negative. It's okay. You get negative 112,500? And this is not my final answer, so I'm not going to round off or anything yet. Direction is none. Going to do the same thing. Find the voltage from charge B. That's going to be 9 times 10 to the 9th. Charge B, 4.2 times 10 to the negative 6, all over 0.24. I get positive 157,500? What's the total voltage at the dot? Add them up. It's going to be 157,500 plus negative 112,500. So this number plus negative 112,500. And I get 45,000 volts even. 45,000 volts. What does that mean? It means if I brought a charge from out at infinity, if I brought a 1 Coulomb charge and plunked it right at that 45,000 volt, at that dot, I would have done 45,000 joules of work. That charge would now have 45,000 joules of potential energy. Now, again, a 1 Coulomb charge is huge. So that's why you have such a big number, too. Derek, what's C asking me to find? Work? Ugh. Work is going to be the change in potential plus the change in kinetic. These are point charges, so I can't use force times distance. I think the question kind of implies we're starting and ending at rest. Certainly doesn't indicate that we're moving. So I'll nuke the change in kinetic. What's changing anything, Derek? Ugh. Oh, hey, wait a minute. Where are we starting out at? What's our initial location? Infinity, which means what? You knew PEI wasn't a real province all along. PE final. Oh. Don't write this down. I started to go K, Q1, Q2, but first of all, if I'm doing that, Hayden, don't write that down. If I'm writing this, Q1 and Q2 are these two charges, and I'm finding out how much energy they have between them. That's not what the question is saying. The question is saying take this charge and move it out from infinity all the way here. This is not going to work. Wait, Derek. What did we find in part B? There wouldn't be a version of potential energy that has a voltage in it, is there? Oh! You mean I can just go and the change in potential will be just the change in voltage? Hey, how many volts are there out at infinity? 0. So, how big is the charge that we're moving, Derek? How many volts are we moving it through? 45,000 of them, thank you very much. And I find that it would take 0.002, I'll call it 2.14 times 10 to the negative 3. 2.14 times 10 to the negative 3 joules of work. Derek, when we solved for B, did we get a positive voltage or a negative voltage? So that makes sense because we're bringing in a positive charge towards a positive voltage. It does not want to go towards the positive voltage. We will have to do work. Mr. Deck, I'm bored. Can I watch TV? Fine, turn the page. Here is our model television. I've given you a side view. So in the side view, we have the accelerating plates. These are the Y plates. They deflect the electron up or down. These are the X plates. They deflect the electron left or right. And let's imagine that we are sitting in a chair watching TV. So we're seeing this. Right now, Matteo, when we first turn the television on, we don't have any of the deflecting plates going yet. And so what that means is we get a white dot in the middle of your screen. Have you ever played with an old black and white TV? So the real old ones, when you turn them on, you got a big white dot in the middle of your screen. It took a while for them to warm up. So right now, the electron's hitting dead center. Here's the first question. Where will the dot end up? We're going to choose from A, B, C, D, or E from this picture here. If I, number 1, make the upper deflecting plate positive. If I make this positive, where will the electron end up? Location A, B, C, D, or E? What do you think? What's the charge on an electron? Negative or positive? Negative. And we've said that now that that upper plate is positive. How will that affect the electron? So, A, B, C, D, or E? You need to deflect it up. Yeah? What if I make this right plate positive? What if I make that positive? So turn the original plate off and just make the right plate positive. Now where will the electron end up? A, B, C, or D? B. You okay with that, Luke? What if I turn both plates on at once? Where will the electron end up? Is that okay? E? Let's tweak it a bit. This time, we turn on the deflecting voltage so that our starting condition has the electron beam hitting right there. What if I bump up, increase the deflecting voltage? Will I end up at A, B, C, D, E, F, or G? What do you think, folks? A, B, C, D, E, F, or G. If I increase the deflecting voltage, is that going to deflect the electron more or less, or stay the same? More. So what will be deflected more? I think location G, yes? Yeah. What if I reverse the polarity of the deflecting voltage? What if I flip the voltage? So let's go back to our original situation and flip the voltage. Where will the electron end up? A, B, C, D, E, F, or G? C? Last one. What if we increase the accelerating voltage? So instead of mucking around with the deflecting voltage, what if I increase the voltage here so that it's going even faster? If you travel faster through the plates, will you be deflected more, less, or the same? Less? So A, B, C, D, E, F, or G? Yep. Says explain your answer using principles of physics. I think we just did. How does this explain how an old black and white TV works? So, one pixel is hit at a time. One pixel is hit at a time. We would sweep the Y voltage up and down, changing it so we can bend the electron up and down, and we would just slowly increase the X voltage. And what you would get is an image as follows. The actual TV screen would paint something like this. Except thousands of more lines than that. But that's how it would trace it out. And as long as it did it fast enough, Sarah, your eye would smooth that into a seamless image. And as long as it did it 60 frames per second, in fact, you wouldn't even notice any jerkiness or distortion. And there's your TV. Oh, beam on is a white dot, beam off is a black dot, beam partially on is a gray dot. I already showed you the high voltage cable inspection video, I believe. And I already showed you last class the monitor teardown, which works with a very different type of technology. So what's your homework? Quiz and ultimate review.